session on probability and statistics. So I'm Young from Statistics Department in Seoul University. Today we have our host speakers. The first speaker is Lyons from the University of Oxford. He's currently the director of Oxford Institute of Convergent Finance, and he got Doctor of Philosophy from the University of Oxford in 1980. He has received a number of honors and awards, including a Lord Davidson Prize in 1985 and Prize of Poyas Prize of London Mathematical Society in 2000. And he has been a fellow of Royal Society since 2002 and was elected as president of London Mathematical Society in 2013. He's a specialist in probability and stochastic analysis, and he's very famous for having developed what is known as the serial log test. And today's talk is also related to this topic. And so the topic is log test, the signature, and modeling of functions on strings. Okay, Dr. Terry Lang.
Thank you very much. I hope to give you a little introduction to a number of things in this talk today. What I aim to do is to start with a relatively general description about paths, which are somehow, or streams, which are somehow at the heart of everything I'm going to be talking about. I'm going to look at certain rather specific features of them and the transform. I'm going to then spend a little bit of time telling you about some features of rough path theory. I'm not going to do what can't possibly be done. And then ultimately I'm going to try and explain why those sew up together to give you an inroad into a certain small part of machine learning. In fact, what I'm going to be talking about is, as with Martin been talking about, how important Taylor's theorem really is. And I hope you see that, in fact, in some way, that is at the heart of everything I'm going to be talking about today. I want to start with paths. Now, I think if you're a probabilist, you think you know what paths are. But actually, one of the things I've learned is that paths turn up everywhere in all sorts of different ways. The picture here is just a piece of text, actually, translated in a particular way so that you can see it visually. If you look at a market or an exchange, you see streams of data coming along, all sorts of things, bid offers, spreads, or bids and offers, and occasionally your purchase, which is what those solid lines are. They represent the times at which somebody's actually bought something. You get very complicated data. So what is a path? For me, a path is a map. It's a map from a totally ordered set into some state space, quite possibly a highly nonlinear sort of state space in general. But if it's not parameterized, for example, if it's a series of letters, then you can easily build another path out of it simply by moving in one axis direction if it's one letter and another axis letter if it's another direction. And that actually turns out to be quite a practical thing to do. Now, I'm very much interested in paths because they do things. I'm not really a painter, my daughter's a painter. I'm very much more interested in trying to understand things because I'm an analyst, because things are related to one another mathematically. And I think this is actually rather a good discipline to think about when we're looking at the problems I'm interested in. So I'm interested in how you describe a path succinctly, but in a way that captures its effects. At the bottom I've listed a number of little examples of things that are ways that, there are paths and the ways that people capture them and the sort of goal they're trying to achieve. And I think generally speaking, there's a sort of feeling and a natural engineering feeling that every one of these problems is different, they're all going to have their own methods, and I'm sure that's true. But there's a bit of them, and that's the math if you like, that turns out to be common, that is shared between many of these problems. And it's that bit that I'm really going to talk about, it's that bit which is rough paths. And although I'm sure you can refine everything I say in particular contexts, I think it's worth understanding that there is a core bit, like arithmetic with numbers, doesn't care what the numbers refer to. And that's really what rough paths is all about. So we think quite abstractly about paths, and but we can go back in the end to some of those concrete examples. And I hope at the very end to give you a real little experiment with real data to let you see that these things can actually be used. So for me, a path is a stream. I'm going to make, at the moment, the situation always where the path is taking its values in a linear space. And I'm going to interpret it, I'm going to model its effects in terms of a controlled differential equation. A controlled differential equation has a certain number of ingredients. Has the path, that's going to be the control. It has a dynamics, which we'll talk about in a little bit, which wrap together to give you an equation for the evolution of state of some system. So y is the system that is responding to the control and has its own natural dynamics maybe. F is simply a linear map from the space where our control lives into the space of dynamics of vector fields on our target space. And when you think about that all through, this all makes sense. This thing here turns into a vector field, and then y can evolve according to that direction over time. So that's the right sort of way of doing it. You can write them in other ways, and they tend to be less helpful. F is a linear map from E into the vector fields on F. And I'm interested in this sort of system. It's surprisingly broad. It captures finite automata in computer science. It captures holonomy in pure mathematics. It captures a very wide range of things in between. Probabilists, of course, are generally quite familiar with this sort of model, but not everybody else is. Okay, now if we look at a very simple example of this, we actually learn a great deal. So I want you just to think for a minute about a very, very simple example, where in fact the vector fields are linear, so it's actually a mapping into a linear group typically, development of into a Lie algebra into a linear group. And the nice thing about that case is actually then the vector is sort of like a linear map into matrices, and we can understand what n powers mean, and you actually apply Picard's theorem, you get something quite, whoops, oh, I don't know how I do that. How do I, thank you. Right, and you get something quite interesting coming out of it, because you get a very clean separation between the vector fields and gamma. And gamma emerges in this rather complicated way as a series of iterated integrals over simplices. And this, I'll go into more detail in the next slides, is actually a very important remark. There is a clean separation between the dynamics and the control. And it is that in a way that allows you to do pure mathematics about the paths without worrying too much about the individual system. And what we'll find later is there are uniform estimates, uniform analysis that you can do, which in the end shows how little what we're doing depends on the particular A or even the particular gamma. Okay, so that's the end of the sort of broad general introduction about paths. Now I want to spend more time thinking about this particular tool, which is now called the signature of the path. And the signature now is something which exists purely on its own. There's no dynamics it's going to contract with. And that sort of makes sense for all sorts of reasons. So if we go back to our sound compression, the engineer actually wants to compress sound in a way that works for lots of different dynamical systems. Every different person in this room is slightly different, and it's really good news that we can think about this thing all on its own. But the nth term is an integral over an n simplex, and because gamma is vector valued, if this is a two-dimensional object, this thing is a 2 to the n-dimensional object, it lives in bigger and bigger spaces. It's quite a big object, but actually computationally you can really work these things out. I was tempted to show you a slide, I have a little computer program that works them out in real time, but I was told I should stick to maths. And this object is a collection of terms, but the generating function, if you like, is a very interesting object in its own right. It lives in the infinite tensor algebra of tensor series, and it solves a differential equation. Okay, and it's actually the fully non-commutative exponential, so you can sort of see that it's sort of bound to be interesting in some ways. But actually it's a homomorphism as well. The tensors are an algebra, you multiply something of length n by something of length n, you get something of length n plus m. It's an algebra, and it's this map from path segments into the signatures is actually a homomorphism. If you concatenate two pieces of path segment, then the signature of their concatenation is the product of the signatures of the individual pieces. So we have this natural map taking path segments onto sequences of tensors. In fact, if you run the path backwards, you get the inverse. So actually the range is closed under multiplication and has inverses, so it's actually a group. And in fact, this is a homomorphism from the monoid of paths with concatenation into the tensor algebra, into a special subgroup of it, which is a dense subgroup of the group-like elements. Okay? So looking back at our linear equation, I want to reinterpret a little bit what we've said here, and I want to emphasize now that in fact what we've done is we've observed that the effect of this path segment, the value at time capital T, can be expressed as a linear combination of these terms in the signatures, or if you like, as a linear projection of the whole signature. And this is actually something quite practical. Expressing something as a linear combination is the whole idea of Taylor series. I mean, Taylor series observes that you have monomials and smooth functions can locally be written as linear combinations of them. We'll see later that this is actually a very powerful idea. And we'll also see, and it's in practice quite amazing, I think, that you can estimate the errors if you truncate the sums. You can estimate them in quite a uniform way that, as I say, is remarkably insensitive to A or to the path gamma. So, but before we do that, I thought I'd just give you a little illustration, a little game, if you like, that exploits the fact that interesting functions can be written as linear combinations of these signature terms, what we would call coordinate signatures, coordinate iterated integrals. Okay? So what I'm going to do is I'm going to look at a function of my underlying path gamma, which is unfortunately migrated in name to x, and I'm going to solve, actually in this case, a nonlinear SDE along the path. Now that's a complicated function, and in fact, Tessie and Papavasilia and Christophe Ledoux had a nice paper in the Annals of Stats where they look at the inverse problem, where they look at the inputs and the outputs and try and guess the equation. I want to look at a different problem side. I just want to learn a function. And it turns out that it's quite interesting to do. So the idea should be that this function that takes you from the path, from the control, onto the response at time t, can be learned very easily. I mean, after all, if something is a linear combination of functions, it's not very difficult to work out which linear combination it is. It's like drawing a straight line to a load of points. And SVD is a standard numerical method for doing it. So what we did is we computed a few terms in the signature of x over this interval from 0 to t, and we computed 800 realizations of the SDE, and we took the pair, the signature of the path and the value of the solution to the SDE at the end of the time interval. And we kept them in two halves, one half to learn the function, one half to see if we've done any good with the function. So basically, we're just going to use least squares. We're not going to do anything fancy. There are better ways of doing things, but least squares is quick and dirty, to try and find our f hat that is the most compatible one between the output functions and the input functions, and then we're going to compare it on the data. So if we plot the pairs yt, y hat t, they should be on the diagonal roughly. And there's going to be two cases. There's going to be the case where, I'm repeating myself here, so I'll just go quickly. There should be the case where we were learning, and there should be the case where we're testing. And you'll see that's where we're learning, and I think it's only to that 3 or 4, we get an extremely good fit, not surprising really, given the theory of SDEs, but we do. And indeed, once we've learnt it, we get an extremely good fit with the data that have nothing to do with the learning. But it's quite a simple exercise, and it illustrates that you don't really need to understand SDEs to model the functions that SDEs model. You can just do these squares and fit a straight line if you understand the right sort of functions to look at on the paths. And I'm leading you slowly, with more detail and more proofs through the talk, to the idea that these coordinate iterated integrals are really the correct monomials on path space. I mean, there are all sorts of issues. Are there enough of them? Are they superfluous? All that sort of thing. And slowly during the rest of the talk, I hope to take you through why they're the right ones. And then finally, we'll look at something more serious. This was all simulated. It works, really, because those iterated integrals in that series decay factorially fast. I mean, you have these things A's, well, potentially those A's are going to grow geometrically. You need something to kill them off and make that series converge. In fact, the iterated integrals have a nice feature that they always decay factorially fast, and moreover, you get uniform estimates on them. It's very easy to understand that in the case where the path has finite length, because if the iterated integral doesn't depend on the parameterization of the path. You can reparameterize it, you get the same answer. So we may as well parameterize it at unit speed if it has finite length. And then, of course, you get this integral here, which you can then say, well, what would be d gamma into gamma dot du? And of course, these things now have modulus 1 if we're parameterizing at unit speed, so we can get rid of them. And we see we're just integrating over a simplex. And when you integrate over a simplex, you always get an n factorial, because there are n factorial disjoint simplexes in the cube. And so this thing is always going to decay like n factorial times the length, and it's a trivial exercise to see it. But it turns out that actually, and I'm going to tell you about rough paths later on, and rough paths are not finite length. You also get a factorial decay there, but in this case it's for more subtle reasons, and basically you need to generalize the binomial theorem to a fractional form, which isn't at all a trivial result. But once you have that result, you can again prove nice uniform estimates, where you see that the nth iterated integral is controlled by the p variation of the rough path. That's the notion I'm going to use for the p variation of the rough path. It's not a norm at all. And again, you get a factorial, but it's a slightly slower factorial, and you get a uniform constant that doesn't depend on anything, including the dimension of your Banach space. So you get uniform estimates again on these objects. So if you now go back to the sum, you get uniform estimates on the errors. So that in itself, I think, is really quite an interesting remark. It tells you, it guarantees for you, that the first few terms in the signature give you a quantifiably accurate representation of that control in terms of its effects. If we know the norm of A, and we know the p variation of gamma, then we know exactly how many terms we're going to need in order to get a certain accuracy in measuring our response. And of course, the factorials fall away very rapidly once they get to the point where they bite at all. So we know there's a certain number of terms we need, and after that we can almost forget everything. And that's quite exciting, I think, because it demonstrates that it doesn't matter, at least at this level, which system you're really looking at. Or at least there is something you can do at this level, and people don't do it, so therefore it's worth doing before you do more sophisticated things. So that's roughly the first couple of bits of the talk, and I'd love to know what the time is. How much have we got? Sorry?
25 minutes.
35 or 25?
25.
35.
25.
25. Right. Okay. That doesn't sound too bad. Okay, so now I want to tell you a little bit about rough paths and take you into the next level of the story. Rough path theory is definitely too big for today. I can only tell you a few things. So what I thought I'd try and tell you is first of all a little bit more about the signature. The signature, as I explained to you, takes its values in a group. It's a very overdetermined system in some sense. That can be extremely useful at times, and we'll see why. But it's also useful to have a representation that is more economical. Now, in fact, the signature always begins with a 1, and then it's a 1 tensor and a 2 tensor and so on. But therefore, I can easily take its logarithm. Because the power series for log of 1 plus something is, of course, the something minus the something squared over 2. We're in characteristic 0, so this works. It converges because this tensor has degree 1 bits, but this is the square of a tensor of degree 1, so it doesn't have any degree 1 bits, it only has degree 2 bits. And the third one doesn't have degree 2 bits. and so on. So it obviously converges in the algebraic sense, and log is well defined. So you can take the log signature. The log signature, because of a theorem of Chen, years and years and years ago, actually lives in the free Lie algebra, generated by E, living inside the tensor algebra. And this is actually a very, very helpful and powerful remark. Interestingly, I don't think it was noticed so much by the ODE community, because actually Chen wrote this paper about a year and a half after Magnus's paper. And Magnus's paper has been used an awful lot, but actually Chen's formulation is a much more convenient and elegant one. But it doesn't seem to be referenced in the ODE community. And I'd like to explain how this fact that the log signature lives in the free Lie elements leads immediately to numerical methods and allows you in the nonlinear case now to understand how the signature is helping you know the dynamics or the response of the underlying system. The point is that in your controlled system, F, you'll remember, is a linear map from E into the vector fields. Okay? The vector fields are a Lie algebra. The free Lie algebra has the property that if ever I have a linear map from E, it'll always extend to the free Lie algebra. So it naturally induces a map from the free Lie algebra and its truncations into the vector fields. That's actually a dynamics. I can take my path, I can compute its log signature, I can map it into a vector field, a single vector field now, using F, and I can solve the ODE. And if I solve that ODE over the whole interval from from 0 to 1, I end up with an approximation for the response. And this is actually a high order approximation. In other words, it works well on small time intervals, and it works very badly on long time intervals, but it has a huge positive effect, as well as being elegant and high order, is that it pushes the numerical analysis onto somebody else. Because it says, if I want to understand my controlled differential equation, I just solve this ODE for a bit of time. Well, fortunately, there's an enormous amount of research into solving ODEs, the symplectic methods and so on. And this actually allows you to have much greater stability than you would if you did Picard iteration and Taylor series. But you begin to see again that the log signature immediately gives you information, accurate information about the response of your system without particularly needing to know which system you're talking about. There's lots again of quantitative uniform estimates that you can build, but they're a little too sophisticated to talk about now. So, if there's some intuitive feeling that the signature is telling you everything, rough path theory makes a difference by actually creating a few definitions, precise definitions, and then proving some quantified theorems. It tackles the question that suppose we have two of these smooth paths, both driving our system, and suppose that those paths are normal scales but very oscillatory. How could we decide whether or not those paths had the same overall effect in broad terms? It's about trying to quantify being close as controls when the data is very oscillatory. Now, the normal way we would say bounded variation paths are close would be if their increments were close and summed up. And in fact, whoops. In fact, that's exactly what we have here if you put p equals 1. If p equals 1, we're only summing up until the integer part of p, so we only have one term in this, and this would just be the total variation norm. But as soon as p gets bigger than 2, you see that actually what we're requiring is a sort of a p variation norm, which is like a bit like a Holder norm 1 over p. A p variation norm, but it involves more than just the increments. It involves these higher iterated integrals up to a certain level. And this actually is the key point. We can write down a family of metrics, and each metric is more relaxed in terms of the oscillations it will allow the path, and less relaxed in terms of what it looks at. It requires more and more information about the signature of the path. In fact, what it's doing, you see, is it's actually paying more attention to the order in which things happen within the path. A chord tells you nothing about the order of the pieces in between. If you shuffle them, you get the same chord. These signatures are actually capturing more and more non-commutative information, and that works in practice, and you get a theorem. And the theorem is that that controlled differential equation is actually a uniformly continuous function in these metrics, provided the vector fields are appropriately smooth. And uniformly continuous means you can make sense of them on the completion, and it makes sense to look at the completion. And that is actually what P-rough paths are. So geometric P-rough paths are the completion of the smooth paths in these metrics. You never actually need to think about them if you don't want to. You can always view it as an estimate that two paths, smooth paths are close in the DP metric, then they will have roughly the same responses provided the vector fields are close enough, and the estimates are uniform. And they're uniform across dimension as well. These things all make sense in balance spaces. So that's, if you like, the core of rough path theory. And the reason it's needed is that actually the control map is a horrible map in classical norms if you want anything rougher than Brownian motion, or as rough as Brownian motion. They're not closed, not closable. So if you look at the map on smooth paths and you look at its graph and you close it, it's not a graph. So in other words, unless you add this extra data in, these iterated integrals, you're doomed. There is no good way of making sense of these functionals if you stay in the world of paths without that extra data. But once you go into the rough path metrics, there's really no trouble. Okay, originally this stuff was all designed to handle problems about stochastic differential equations and lack of continuity, but very quickly one realized that there were lots of other examples. Brownian motion itself is an example. In fact, so are fractional Brownian paths for first index less than 4. That hugely already extends ethocalculus. Ethocalculus is well known to only deal with semi-martingales, and there's a much broader range of processes than that, but there are many others as well. You have a sort of semi-martingale property where you can integrate and build new ones out of old ones. A very important feature that I made use of implicitly, but has become much more valuable since Goupil made use of it explicitly, and Martin has made incredibly good use of it in his much more deep and complicated PDE examples, is that once you fix on a rough path, then as you iterate or whatever, all the new paths you get are intimately related to the existing one. And although this group or whatever of rough paths is a nonlinear object, there are all these linear spaces that are sort of tangential to the path you already have. And that's actually a rather important practical feature of how you make the analysis work. Well, okay, so now I'm more or less going to try and explain how that actually fits into machine learning, and I'd love to know how much time I have again.
15.
1.5.
15.
Perfect, thank you. Okay, so this has two parts really. It has a slightly theoretical part, and then finally a genuine experiment to see how we go. So, a key idea in a lot of real machine learning type things is that you want to learn functions. You have a series of evaluations or pairs, yn and gamma n, and you'd like to learn how to model f. We've already seen that in the case of an SDE, this was an incredibly simple thing to do, providing you on relatively short timescales. I want to explain to you now why signatures are just the right sort of object to get going on this. I'm not claiming that what I'm going to tell you is state of the art, rather the opposite. I've deliberately just used least squares and things because these are naive. There are actually much better ways of using features than the ones that I'm talking about, relating to support vector machines, deep learning, and so on. I'm not touching on those because I just want to establish that one can get going. I'm not an expert in all the other bits. But a key trick in almost all of these, whether it's Taylor's theorem modeling smooth functions, or maybe rough paths and coordinate iterated integrals, or even more complicated things to do with shape, with Smaler, a key feature is that you have a collection of, sorry, I shouldn't use feature. A key point is that you have a collection of functions, which the computer science and stats people tend to call features, which are a way of describing gamma. And you don't know gamma exactly, you never will. Or maybe you do, but I mean, you have these features of gamma, and the idea is that you hope that your function, f, can be expressed as a linear combination of these feature functions. In other words, somehow they're rich enough to express any function as a linear combination of them. And if you believe that, then actually it's essentially linear algebra if there's no noise, to figure out what the lambda i's are if you have enough samples. As long as you have more samples than the dimensionality of the problem, you're going to be able to do it. And you can do all sorts of intelligent things even if you don't. But so the idea is that you want or hope that your function is a linear combination of these feature functions. And this is actually the heart, in a way, of rough path theory, and it's the heart, in a way, of regularity structures too. That you need to be able to find an appropriate class of functions that, in some sense, well represent the functions of your object locally. Now, if you were doing kernel methods and things in statistics, I think you miss a valuable point. If you want to be confident that this is a rich enough class of functions and you want to do it more, at more points than the gammas you've already seen, then you would like the linear combinations of the phi i's to actually span the space of functions. If they don't span, there are clearly going to be serious obstructions to doing this. If they don't span quickly, there are going to be serious obstructions to doing this quickly and accurately. And one of the most standard ways to get a rich spanning class is if the phi i's span an algebra. Because then we had Stone-Barström or its equivalents. That's why monomials work. Monomials work because they form an algebra. So I want to now be a little bit more formal and point out that the coordinate iterated integrals form an algebra. This is actually well known if you are in the world of tensor products, and it relates directly to something called the shuffle product. But a coordinate iterated integral is simply a projection of my signature onto scalars by some linear element in the dual space. We may as well just choose basis elements. And you can see why it's called a coordinate integral, because it's essentially taking coordinates of my path and integrating them. Now, that's a real valued function on path space. If I multiply two of these together, that's algebra property. If I multiply these two together, it actually works. It works quite well. Because by Fubini's theorem, I'm integrating over the product of two simplexes. And if you think about it, the product of two simplexes can be decomposed into a disjoint union of simplexes. And that's actually obvious, and you do it by shuffling the two sets of times in every possible way that preserves the order of the first one and the order of the second one. It's called shuffle product. So actually, it's completely obvious that you have this identity that if you evaluate phi e on gamma and phi f on gamma, then you get the same thing as evaluating phi of the shuffle of e and f on gamma. So indeed, you have this algebra structure. In fact, the algebra structure is not at all surprising. If ever you have a group, and we had a group here, and it's in its enveloping algebra, and the tensor algebra is well known to be the enveloping algebra of the group-like elements, then the pre-dual always has a natural abelian product structure on it. And that's actually what we're seeing here, and that's what you see when you do polynomial regression, when you use polynomials to do nonlinear regression on R, and that's also what you use if you were doing more complicated things to do with shape, with Smale and people like that. So it's a general principle that this is what you do. But one might still have problems because it's not actually obvious that the signatures themselves separate the strings. So if you want Stone-Barström, you want an algebra, but it should separate the points. It's obvious that the coordinate iterated integral separates signatures, but it's not obvious that signatures characterize paths. Now, there was a paper of myself with Ben Hambley which took like 6 years to appear, but appeared in 2010, which shows that the signature of a path completely characterizes a path of finite length up to a generalized form of reparameterization, which is called tree-like. It was open for some considerable time, whether that was true for rough paths in general. The whole statement was clearly sensible, but recently I'm pleased to say that my postdocs, with a little bit of help from me, have nobbled this problem. So indeed it does separate path streams up to reparameterization, and therefore, in some quite natural way, is an appropriate class of features to really look at functions on strings. So let's actually try to just put it into practice at a really simple, naive exercise. So one thing you might try to do is classify strings. In practice, understanding time sequential or time evolving data is a really important problem. And one of the things you would like to be able to do quite often in lots of different contexts is simply to classify, break it up into groups with property A or property B or whatever. This was our first game we ever played with this. And what we did is we took some financial data from oil markets, or future markets, and then we broke it up into 30-minute pieces, and we tried to see if we could tell what time of day it was from the data. It's too easy if you don't renormalize it to get rid of volatility and everything like that. So we renormalize it to get rid of all the obvious things. And then we simply take a very simple function, which is 1 if it's in one time slot, and 0 if it's in the other time slot, and looked at the data from the pairs, and just try and learn it. So in other words, just try and write the function which is 1 on one and 0 on the other as a linear combination of our signatures. This is about as naive as you could get. Again, you can do more clever things. On this particular problem, we got Ben Graham to do more clever things, and actually he didn't do any, he got the same result as us, essentially. But, so we try to fit our function, which takes the value 0 and 1, to a linear function of the signatures. And we're going to do linear regression. But actually, we're also going to use lasso, which is one of these L1 constrained optimization techniques where you do least squares subject to an L1 constraint, but then you optimize where you put that constraint using cross-validation to get the best sort of choice as to shrinking it onto a small number of variables. This is pretty standard. And then we just apply various statistical indicators to see how well we do. And here's what we get. So you see, here is the learning set. This is where we're struggling to find the linear combination that produces a function that is 0 if it's blue, and 1 if it's green or orange or whatever colour it is. And you see, actually, they separate quite nicely. You can certainly do it, but it's certainly not exactly 0 or exactly 1. But having selected our coefficients, found our function, we now looked at it with the completely independent data, and you see there's a striking difference. I should add, there's a striking difference between these 2 times a day and no difference between other times of day. It turns out these 2 times a day are special, the rest of the times are completely indistinguishable from each other, and I'm just showing you how this one fell out. But with a 9/10 probability, it was very easy to do this one, and here is what's called an ROC curve, which is the false positive rate against the true positive rate, and you look at the area underneath. Again, you see that the learning set, which you expect to do well in, isn't doing any better than the out-of-sample validation step, which means we're not overfitting, and it also means that we're getting good information, really, and it just fell out. But, using the lasso allows one to also develop visualization tools because it picks out particular projections, particular sets of iterated integrals that are informative, and then you can see that actually it gives you visualization tools, which you can very easily see the shift in the behavior according to the time of day. But now, just to show you that in general that wasn't the case, here is the same strategy all done for other times of day, when you really can't tell the difference. So it was interesting to us to understand why that was, because we just hit the data and suddenly these two sides of data seem special, and we think it's actually because Chicago still has an open outcry for these markets, and the opening and closing of the markets happens during those windows of time. But from our point of view, it was just a first attempt at hitting real data with what seems like a very simplistic approach. In practice, we've now tried it on a number of other areas, some from brainwaves and so on, and it seems that with a little bit of care, it's remarkably simple but effective at understanding and segregating data, which is time evolving. That's probably more or less all I want to say. How many minutes have I got left now?
4 minutes.
4. So I should thank everybody who puts money in. That's always very important. And I should thank even more the people who have collaborated with me over time, and there's too many of them for me to thank them personally, but frankly the way I work is I always talk with everybody and they talk to me, and I should think 90% of everything I've ever done has depended critically on everybody else. I thank them all greatly. If you want to find references for much of what I've been talking about in much more detail, there's an archive paper which is a publication that's going to appear here. And of course there's several books on the subject, and I was asked by OUP to tell you, but I don't take any responsibility for it. They're flogging off my book for 35 quid if you tell them at the stall, the one with Kian, but I really don't care. So that's all I really want to say right now, and I thank you all very much for listening to me, and I'm happy to answer questions if you have time.
For questions and comments? So everyone understandable. Okay, there is a question from organic committee, so I would like to send it to you.
Thank you.